Hi, I'm Chen Min from Huazhong University of Science and Technology, and I'm glad to share our CVPR work, Boundary Unlearning. Machine learning is gaining increasing attention due to the practical needs of the right to be forgotten and the poison data removal. Machine learning enables ML models to unlearn or to forget a fraction of training data and its lineage. In this paper, we propose boundary unlearning, a rapid yet efficient way to unlearn the forgetting class from a trained model. Boundary unlearning achieves efficient machine learning from the perspective of shifting the decision boundary, which is different from previous parameter-oriented approaches that are computationally expensive due to the large dimension of the parameter space. Now, let's dive into detail of boundary unlearning. First, we will show you why we need machine learning. Recently, DNNs has become ubiquitous tool in developing data-driven services. However, DNNs are powerful yet mysteries. The power of DNN lies in the large dimension parameters, which makes it difficult for us to understand. Specifically, we can't understand of what knowledge the model has learned from data and where the model stored the knowledge. Thus, DNN may cause some unintended memorization, which contains some sensitive or flawed data and will bring security risks for DNN service. For example, a well-trained DNN may remember sensitive data like credit card numbers or facial information of users, which may cause leakage of privacy information. Thus, a lot of privacy regulation have been conducted, such as GDPR and CCPA. Both of these regulation gives individuals the right to be forgotten and mandate the companies to have to erase personal data once it is requested. To solve these problems, a live yet optimal way is retraining model from scratch with the remaining data, but is expensive in terms of the cost of training time and resources. This practical list call for efficient machine learning techniques, which enable ML models to unlearn or forget a fraction of training data and its lineage. Existing unlearning methods for DNN can be broadly categorized into two groups: retrain, acceleration, and updating parameters. Retrain acceleration approaches have to intervene the original training pipeline and hurt the utility of DNN model. And previous updating parameter approaches cost too much computational resource because they need to locate and scrub the most influential parameters in terms of forgetting data. We follow the updating parameter approaches because this branch of a method is more practical for machine learning service online. But the problem is how to reduce the computational complexity of updating parameter-based unlearning approaches. In order to find the efficient unlearning approach to forget an entire class, we visualize the decision space of retrained model and discover two key observations. First, the forgetting data spread around the decision space of the retrained model, indicating that the decision boundary of the forgetting samples have been broken. Second, most of the forgetting samples move to the border of other clusters. Based on our key observations, the utility and privacy guarantee can be achieved by boundary shifting. Hence, we can't help wondering that do we really need to exploring the whole parameter space directly to forget specific information of DNN? As we all know, decision boundary is an important manifestation of DNN. Besides, decision boundary is dominated by the parameters. In the light of this idea, we transfer our attention from parameter space to decision boundary, which is a new perspective and different from previous parameter-oriented approaches. Observing that imitating the decision behavior of retrained model is able to accomplish the utility and privacy guarantees of machine learning, we designed two strategies to shift the decision boundary in boundary unlearning: boundary shrink and boundary expanding. Boundary shrink breaks the decision boundary of the forgetting class by splitting the forgetting feature space into other classes, while boundary expanding disperses the activation about the forgetting class by remapping and pruning an extra shadow class assigning to the forgetting data. An intuitive way to break the decision boundary of forgetting class is fine-tuning the original model with random labeled forgetting data. However, random labeling will also shifting the boundary of remaining class randomly, leading to the degeneration of utility on remaining data. We thus propose a label searching method to identify the nearest but incorrect class label to guide the way of boundary shifting. Specifically, we first push the forgetting data across nearest boundary, and we take the predicting labels of cross samples as nearest but incorrect labels. Then we fine-tune the original model with a pair of original forgetting data and the nearest but incorrect labels. Although boundary shrink achieves both utility and privacy guarantees well, it may cost some time during the label searching. So we propose boundary expanding, which aim to imitate the decision behavior of the retrained model even more quickly. Recall that we start from the observation that most of forgetting sample moves to the border of other clusters on the retrained model. This phenomenon means the forgetting data are predicted as other class with low certainty. As for a single sample, low certainty represents the output vector is more even. More specifically, we first introduce an extra shadow class to expand the decision space. Then we fine-tune the expanded model with the forgetting sample reassigned with the shadow class label. From now on, we will show some evaluation results. We conduct experiments on CVPR23 and VGG phase 2 datasets to test Unlearning performance on image classification task and face recognition task. We first verify the utility guarantee of boundary Unlearning. From the result, we can observe that boundary shrink harms the information of remaining data to the least extent and erase forgetting data most completely. Similarly, boundary expanding also maintains the accuracy on remaining data. Next, we turn to evaluate the privacy guarantee. Ideally, a forgetting procedure should have the same attack success rate as a retrained model, which is represented with the green lines. As shown in the figure, boundary Unlearning can achieve quite close ASR to that of the retrained model on both datasets. We also report the data consumed by each Unlearning method to show the computational complexity. From the third figure, we can find out the method achieved Unlearning quickly. From the visualization of decision space, we can find that the forgetting data has been predicted as a nearest cluster after applying boundary shrink, and some hollow circles move to other clusters. We observed that boundary Unlearning makes the distribution of model's outputs on forgetting data more even, which means the model is less confident about the prediction. We believe that the change about the distribution is caused by the shifting of the decision boundary. Also, we test the impact of number of forgetting sample needed, and we find that boundary shrink can still forget the entire class with less forgetting samples. From the result of boundary Unlearning method and their combination, we can tell that it may be the best combination that first disappearing the activation about forgetting data by boundary expanding, and then clear away the residual information by boundary shrink. For more details and the result, please check out the paper. Thanks for watching.